Today's episode is about loop engineering and harness around AI agents. If you are not familiar with these terms, don't worry, by the end of this episode you will learn about these terms and you will be able to hopefully design some of these or build some of these from scratch yourself. But before I start getting technical or get into the coding aspects, I want to understand one thing. I want to understand how people think about AI agents and their use. And that's why today I'm in center of Stockholm, beautiful city of Stockholm, to ask people one question. If an AI agent could do your job better than you do, should your employer replace you?
They could, absolutely, but my job is a little bit harder than that.
They could replace me, but at the end of the day, you're still not going to get that human experience.
Maybe not, because I need my money. I think that people need to work because you need to stay human.
Still, humans have to do some kind of jobs.
Do you want to answer too? Or it's okay.
Yes, probably. Yes, I think so.
I think he probably should because it has many effects on his cost and his expenses.
I think, if it could do better than me for free, as an economic standpoint, yeah.
I can admit this is a controversial and hard question. And thought-provoking probably. You may think, how is this related to, loop engineering or AI loops? And maybe you think that this is unrelated. Well, it's actually very related. The reason is, loop engineering is discipline of, creating harness around AI and making sure that AI have a system to act upon. When to make decisions, when to let a human step in, when to ask for help, when to stop, and overall, it needs to have some control over what it does. And that's why I want to see what people think about questions such as when it is safe to use AI, and every answer that I'm gonna hear today is going to be an engineering requirement to be, or at least can be translated to one, to make sure that the AI loop that we are designing is safe and harnessed. So let's start. Alright, so may I ask what's your name?
I'm Megan.
My name is Bala.
Christopher.
And my name is David.
My name is Martin.
May I ask what's your occupation or your skill that primary?
Well, I'm an actress to start off with, but at the moment I work for a property management company in the UK, based in the UK. Yeah.
My job, I work in a bank.
Alright.
As today, as an advisor.
I am a mover. I move houses and shops and everything.
I'm a mechanical engineer and work with when things break down.
I'm a project manager in construction.
The topic of today is about AI and the harness around AI and the human-AI collaboration. The question is, if an AI could do your job better than you do, should your employer replace you?
That's a good question. Well, I think, first of all, if I'm speaking as an actress, I believe that AI cannot do my job better than myself. I know that for a fact. I think with AI, you lose that human connection, which is so crucial and important, especially when it comes to acting and reaching an audience, basically connecting with an audience. So I know that I would not be replaced in that era, or in that area rather. But in terms of with property management, sure, I guess if AI did do my job better, they could replace me, but at the end of the day, you're still not going to get that human experience, Like with my job now as a property manager, I speak to a lot of guests one-on-one. I hear their concerns, I can feel sympathy and empathy for them, whereas with an AI robot, you're not going to have that same experience.
They could, absolutely, but my job is a little bit harder than that, because I have talked to some customers and they always say that it's very hard to go in and get to answer fast if AI get to answer, because they want to talk with a person, and sometimes when you send in an application, for example, you cannot see the whole picture. You need to like have a meeting with the customer and see if
Fair enough.
Yeah.
But what if an AI agent still compassionate enough or whatever could do your job better anyway?
Yeah.
Cheaper, faster, better. In that case, should they replace you?
If I was like the head of the company, absolutely, I will not give my employer fire, but maybe see if I can place them somewhere else, for example.
All right.
But absolutely, yeah.
That's a hard question. If it could do better than me, and it's a very hard question, because then you have to drive it and everything. But if it could do better than me, I think if it could do better than me for free, as an economic standpoint. Yeah.
I can admit this is a controversial and hard question,
Yeah,
and thought-provoking probably.
Yes, probably. Yes, I think so.
You think so?
I think he probably should, because it has many effects on his cost and his expenses he has for me. He doesn't have to pay my monthly payment that he pays me. He doesn't have to pay insurance for me and so on.
Okay, fair enough.
Maybe not, because I need my money. And I think that people need to work because you need to stay human. Yeah.
I think that some jobs can be replaced because AI can do it better, but still humans have to do some kind of jobs. And even if the AI can do it a little bit better, humans still need to work, I believe.
All right. Do you want to answer too, or oh, it's okay? If other business, your competitor, starts using AI and goes ahead of you, so you start losing markets because of not using AI, then what? Then what should we do then?
You need human in the world to work, because, well, I don't want the world to be all just about AI, because I don't want robots to run the world, you know. Yeah. So I think that humans should still work. Also, if AI did a better work.
Even if it's cheaper and better.
Cheaper, you know, some humans could still work, and you can use a little bit of AI.
If you think that AI can potentially be better or necessarily cheaper and faster, whatever,
Yeah.
And you think that then it makes sense to replace humans, as you said. What if something goes wrong? Who is responsible?
Exactly. Well, that's where I then don't fully agree with replacing human beings. And with AI, I mean, anything can go wrong. It's a robot at the end of the day, and then who is held responsible? So yeah, to an extent, no, I don't think that AI can replace human beings. No.
Yeah, it's the head of the company, because they have choose to fire all the employees, and if they do that, you cannot point finger to an employee. You need to point the finger for the person who are head of the company.
What should happen then?
That's a good question. I think you need to look at the AI bot that you have, see what was the problem with that, and see if you can fix it. But the one who are head of the company needs to take the responsibility.
That's a hard question. It's the company, because
The company who built the robot or AI?
no, the moving company, because you have to have, because when you move stuff, you have to have, make AI, you have to have the confidence and having to change it. So you cannot just say, oh, well, it's not our fault, it's this one. You still have to have, and I think it's built, you have to have a lot of trust in it to just switch everything.
Oh, it's a good question, of course. I think the responsibility should be for the person who forward the report from AI. I mean, if the AI compiles a report, and then if the human being will sign and apply or agree in the, I think maybe the human.
Well, it's a AI agent, so of course someone builds that AI agent and then deploys it, but then when it's running, it's autonomous, no human is there. So I think maybe what you're trying to say is that maybe the company or the organization that builds that AI might be responsible. Is that what you're trying to say?
No, I think the human being who approves the work from AI.
So a human should review it.
Yeah, he must review it and check.
All right. If that's the case, if another company deploys an AI system that is very robust and very good, but don't have this human in the loop, but then goes way ahead of you, where should we draw the line?
Oh.
Is a good thing to.
It's of course a good question, and I don't think that very few people has the answer.
Yeah, maybe that's a difficult question. I think maybe in the future there will be some kind of like special insurances for that. Like that could be a possibility that you have insurances that cover these kinds of faults or defects from the AI.
The humans, because
And what should happen? Someone gets hurt.
maybe not work with AI anymore. Stop working with it.
Okay.
I think the programmers of the AI should take the consequence and develop it more. And also you can use, for the question you asked before, partially blend in AI, but still have human work also.
And who is going to make sure that fix of the problem is in place? And
I mean, the developers of the AI,
Is that enough?
the ones that knows the code, and not someone who doesn't know the code, of course.
is that enough to say if something goes wrong? And probably some people gets hurt because of that. That company or the person who is, you say, responsible should get fined and then maybe to go to court or whatever. Okay, yeah. Is that enough for just do some mistake and then pay for it? Is that good enough, or other measures should be taken?
I think you need to restrict AI a little bit, not give them all the choices an employee can have. Like, for example, you can give them a job for 1 month and see if they can fulfill it. If they can do it, then give them more responsibility.
So only replace when it's safe. And
Absolutely.
who is measuring that, you think?
The boss of the company.
Is that enough, you think?
Yeah, I think so. Bottom line, regulations. If you have some regulations, I think the state could also go in and look and see if it's a good choice to give the AI full responsibility for a company or not.
Somebody got certs, then I think it's you either take away the AI, not permanently, but just to look what went wrong, what can we do better. So I don't think if somebody got sometimes everybody got to get hurt. It's the human nature. But if you can find if the problem, find it and try to fix it the best you can, because that's everything you can do.
So you think there should be some checks and balances and control over the safetiness of AI, and then only if it's safe we use, and if something goes wrong we check if that problem solved.
Yeah.
But then who is going to do that checks and balances? Like, who is responsible for doing those checks and balances? Is it independently or by company or?
I think it can go two ways. The big opponents just normal Joe cannot just go in and program an AI. So I think you have to have a teamwork between the big companies and everybody else. Because if somebody has a problem, yeah, you can go to the big one and they can do, okay, here's the problem, we can fix it, we can make it better. But you also have to have, like every equipment, you have to have safety control on it. Because if somebody maintenance and everything, you have to have checks if it works right, so it doesn't go to the place where something goes wrong and somebody's hurt, something get damaged. So you have to have organization, I think, that makes things people do those checks and can control what people do them and what checks they have to have and everything.
Yeah, I mean that would be kind of I see your point. Like if people get involved, it's more difficult because it's not only like it doesn't only cost money or something gets broken, but if people are in danger because of a decision that AI makes, then it's more complicated, and then that should be not done by AI, I think. But also on the other hand, people can also make mistakes. So
you draw a line there. You say, okay, if there are humans involved or human life involved, we should do something else.
yeah,
What is that else thing that we should do other than insurance then in that case, you think?
I mean the other way would be like the traditional way, like not using AI, but then people also can make mistakes. So then it's just a person responsible for it. So you have somebody that is basically responsible for it instead of AI not being responsible for anything.
All right, so not using AI, doing traditional way. But then what if a competitor of you use AI and don't have those guidelines and just go ahead full speed and goes way behind you, almost win the game? So you go way behind, because you keep yourself way behind just because you don't want to use AI because you think it's not too safe. But your competitor winning the game. What should we do then? What is the solution here? We don't want to go out of business, right?
Yeah, then it's maybe also it has to do more with explaining the clients maybe, or also it pulls into like the marketing maybe, where you tell your clients that you are really keen on just perfecting this kind of still like traditional way of working, and that other competitors don't do that, and that there are risks involved with that, but that your firm is very focused on maybe not using AI in specialized areas.
But what if in a competition, in market,
Yeah.
some companies started to use AI
Yes.
and they started to go ahead, get ahead, win the game.
Yes.
In that scenario, it sounds like it's getting very tense to not to choose AI.
Sure.
If there is one rule for you to replace humans with AI, in case it's possible, what would that rule be?
Ooh, that's a very good question. I think to have a bit of a balance. If you're gonna replace human beings in the workplace, I think you should have at least a balance. Maybe half AI, half humans at least. You have to have the balance at least. I think that should be the rule. I know if people are getting ahead with AI and so on, and they are being more successful and whatever, and more efficient and all those things, I can understand that. But at the end of the day, there's also cons to that, you know.
Why do you think a balance is necessary? Like 50% human, 50% AI?
Well, at least for me, I enjoy the human experience. I don't like speaking to a robot or getting information from a robot. I want to speak to someone and hold someone accountable for anything. If I've ordered something, it's come too late or whatever, I want someone to speak to me and tell me what's going on or how we can figure this out or how we can move forward. I don't necessarily want to speak to a robot that's going to tell me, oh, sorry, a week from now you're going to receive it or something, you know?
Is it fair to say only replace humans with AI if it's proven safe and ethical?
Is it safe to say that?
Yes.
No, I don't think so. Yeah, no. I don't think we should lose that human connection. I think that's very important, and especially today, we've already lost so much of it with everyone being on their phones and social media and stuff like that, and we're just moving so far in that direction. I think we should be moving back to connecting with one another and helping each other. We don't need robots. We're smart enough. We can just help each other, you know, and yeah, that's what I believe.
Thank you so much for your time.
Thank you.
Thanks.
That's a good question. That's a good question. I don't know really. Like I said, if they are faster, better, and give you like better result than a person, then absolutely, I would do it.
Thank you so much for your time.
You're welcome. Thank you.
If AI can become so smart, right now it cannot. Some jobs it can, not really good. But if it can do cheaper and greater work than a human being, at some jobs, yes, you can switch to it. So I think a rule is, can I trust this 100% or like 99% to do the work and do it fine?
I'll be safe.
Yeah, that's like my one ground rule and everything.
Right. Thank you so much for your time.
Yeah.
I think I prefer at least a few more years that a human is in the loop. What happens in 20 years? I have no idea.
All right. Thank you so much.
Thank you. Please meet you.
Thank you.
Thank you.
For the humans to still have some kind of income or help to get a new job, just so that you don't see more homeless people and unemployed.
All right. What will be yours?
I think the same as him, you know, we still need to get some money and we don't want the world to be just all homeless people and
So the government should maybe do something about
yeah.
that circumstance, and also the only replace maybe when if it's safe.
Yeah.
Probably. All right. Thank you so much.
Yeah, thank you.
Would you think if we find a way to guarantee, or not necessarily guarantee, but have a good checks and balances for AI to be used safely, then maybe we should probably then enable it for human use? Do you think such thing can help in that case?
I think it will not like it wouldn't actually be a question if we should do it or not, but I think it will be something that happens automatically because it gets less and less expensive. And then if it gets less expensive and faster, companies will do it like anyway, and probably they will take some risks for it. So I think maybe it's inevitable. So it will happen, and probably nobody will ask the question, should we do it or should we not do it? Right.
Thank you very much.
Thank you.
Thanks.
Perfect. Thank you.
I received very interesting answers in this interview. What started as a simple yes and no question became much more complicated. Some people basically said, yeah, let's replace humans with AI. Why not? It's how business works. If it's cheaper, faster, and better, let's do that. But some others said no. Work is not only about efficiency, it's also about income, dignity, trust, and human connection. But the most interesting part, at least for me as a computer scientist, was when I started to, push the question a bit further. I started, if you follow the interviews, I started to ask, What happens if an AI makes a mistake? Who is responsible? The company using it, the people who built it, the person who approves its work? Should someone review every single decision? Or should AI given full responsibility? Or should it begin with a small amount of responsibility first, prove itself, and earn more autonomy over time? And who decides when it's become safe enough? That is where all these questions and this interview directly connects to loop engineering, which is the topic of this episode. Because all of these concerns eventually become decisions that we have to represent in an agentic software system. When someone says it should prove that it works, if you follow the interviews, it means we need a verification loop. When someone says a human should check the results, we need a human approval step. When someone says give it a limited responsibility first, we need stage autonomy and restricted permissions. When someone says if it fails, stop it, investigate what happens, fix the problem, and make sure it doesn't happen again, that may become a repair loop or an incident response loop, depending on situation. Or when someone says the company should be the responsible party, it means our agentic system needs to have logging, traceability, clear permissions, and evidence of what that agent, or in collaboration with human, both of them actually did throughout the software engineering process. Now, of course, not everything you heard in these interviews or people generally raise in this topic can be solved by Python or by coding. Questions about employment, human income, human dignity, law and regulation are much bigger than software architecture. But the technical part is still our responsibility as software engineers and professionals. We decide what agent is allowed to see. We decide which tools it can use. We decide what happens after it takes an action. We decide how its work is being tested, what it remembers, when it retries, when it stops, and most importantly, when it's the right time to replace a task that usually humans do with the AI version, or vice versa, hand control back to humans. Sometimes that system can be described as a relatively simple loop, but sometimes it contains several loops inside one another. If you follow the news, increasingly people start talking about something called graph of loops, where several feedback loops interact, supervise one another, and pass work between each other. We will come back to that later, but first and foremost, I want to go through basic vocabulary. What exactly is a model? When does a model become an agent? What is the harness around that agent? And where does the loop actually lives? So let's get started.
A language model receives an input and generates an output. An agent uses that model as one component inside the system that pursues a goal. The harness is the software surrounding the model. It decides what the agent can observe, what enters the context, what tools exist, what state survives, what actions are permitted, how results are verified, and what happens after every single action. A recent 2026 survey proposes exactly this model harness perspective. It describes an LLM-based agent as the foundation model coupled with an execution harness, and decomposes the harness into 6 distinct responsibilities: observation, context, control, action, state, and verification. This distinction is fundamental because when two products use the same model but achieve very different results, the difference may come from their tools, their files interface, their context policies, their retrial strategies, their verifier, their memory, or even maybe their stopping rules. The model matters, but the model is not the entire agent. Before we define loop engineering, it helps to separate it from three neighboring ideas. Prompt engineering asks, how do we ask the model? Context engineering asks, what information does the model receives? Harness engineering, which to be fair is older than the others, asks, what can the agent observe, remembers, and do? Loop engineering, on the other hand, asks what repeatedly starts, directs, verifies, remembers, and stops the work. The phrase loop engineering is fairly new. I was reading a paper last week, which was published, I guess, June 2026, called Stop Hand-Holding Your Coding Agent, proposes a specific artifact called loop specification. A loop specification contains 5 basic elements: a trigger, a goal, a verification step, a stopping rule, and a memory. The specification is then executed by an agent harness. That qualification matters because loop engineering is an emerging technology. There is no single universally accepted textbook definition, and there is no officially approved final list of potential agentic loops one can design or have. For this episode, I will use a practical definition. Loop engineering is the design of repeated, feedback-driven control around an AI model. That design answers almost 10 or 9 questions. I guess 9 questions. What starts the work? What state is observed? Who selects the next action? Which tools may be used? What feedback returns? What memory survives? How a success is being verified? When does the execution stops? And to me, the most important part is when does the human intervene? This definition covers both the internal control cycle inside one agent run and wider operational system around repeated runs. That gives us a useful way to study real architectures without pretending that the terminology is already settled. Before we get into the architectures, we have to solve the terminology problem. People often use the word loop in 3 different layers of an agentic system. A recent loop engineering position paper separates 3 meanings that often gets confused. And it's very important to mention that this is not a claim that there are exactly 3 loop architectures exist, and it's just that it's kind of like a scope distinction between 3 uses of the same word. The first meaning is an ordinary programming loop. Imagine a code that iterates over every file and directory in your computer and inspects each one. The developer have already specified the repeated operation and conditions for stop. That is like a normal deterministic program control flow. The second meaning is an internal agent environment cycle. The agent observes the environment, selects an action, performs the action, receives a new observation, and then selects another action. This interaction model is much older than modern language model agents, and Sutton and Bartow presented canonical version of this in Reinforcement Learning, an introduction book. In that model, an agent observes a state, chooses an action, and receives a new state and reward. Modern language model agents uses related state observation pattern. For example, React, another paper, interleaves the modern reasoning with actions that retrieving information from an external environment, and those observations then influence later decisions. For coding agents, the internal cycle might be read the issue, search the repository, read the file, edit the code, run the tests, observe the results, and choose another action. That's an example. These cycles inside one bounded task execution, for example. The third meaning is the external operational loop. This loop sits outside one agent session and decides when the run should begin, which task should be assigned, which harness configuration should be used, how the complete result should be verified, what information survives between runs, and also when the system should publish, retry, escalate, or discover new work. Consider, for example, continuous integration failure. The external loop perceives the failure, creates an isolated workspace, and start the coding agent. Inside that run, the agent searches, reads, edits, tests, and repeats. When the internal run ends, the external loop verifies the complete patch and decides whether to open a new pull request, retry the refresh context, or escalate to a human developer in that case. So these are not three competing architectures, and there are not the only loops that exists. An ordinary programming loop implements deterministic repetition. An internal agency cycle coordinates the actions during one task, and an external operational loop coordinates complete agent runs over time. A real production system may contain all three at once. Imagine that I ask a model to fix a bug. The model generates a patch, returns it, and stops. The flow is very simple: task, model, output, stop. That is open loop generation. The system has not checked whether the patch compiles, it is not running any tests, it is not observed whether the application still behaves the same as before or correctly. On the other hand, the closed loop adds feedback. The system receives the tasks, generates a patch, runs the test, observes a failure, revises the patch, and the important property of this is not the repetition. The important part is that the result of one attempt changes the result of the next attempt, or the decision making in the next attempt. Calling the same prompt n times is repetition. Returning evidence from attempt 1 into attempt 2 is feedback. That difference is the foundation of everything we build from this point on in this episode. There is no universally accepted finite list of every possible agentic loop, at least according to the research that I have done. And to me, different researchers classify systems according to the research questions they are pursuing at the time. For example, I was reading a paper about a survey in planning in language model agents, and they were grouping planning research into task decomposition, plan selection, external module assisted planning, reflection, and memory. That's pretty useful for that particular planning problem, but to me, that's not a taxonomy of every loop in every single agentic system that you can find in industry. To me, the lesson is pretty simple. A taxonomy depends on the layer and the research question. So the dimension I use in this particular episode are just an organizing framework. They are synthesis of recurring design decision in research and not an official universal standard. If you follow the news, there is also a recent phrase worth discussing called a graph of loops. Peter Steinberg, which is the creator of famous OpenClaw project, asked on, I think, X, are we still talking loops or did we shift to graphs yet? Precise answer, I think this is a very interesting question, but to me, the answer is, with all due respect, is that graphs do not replace loops. A loop is a feedback mechanism. However, on the other hand, a graph is an orchestration topology. A graph of loops connects several bounded loops, one-shot operations, verifiers, reviewers, and human gates through explicit dependencies. So imagine a planning loop that launches two implementation loops in parallel. Their results converge into, for example, a verification loop. The verified candidate moves into a review loop, and the high-risk result may end at a human approval gate. In one model controlled loop, a single active controller usually chooses the next action from one growing context. In a graph, on the other hand, the different nodes can have separate state, permissions, budget, and verification rule. They can run sequentially, in branch, execute in parallel, or converge at an arbitration step. A 2026 position paper called From Agent Loops to Structured Graphs proposes a structured graph harness. It places ordinary agent loops and graph-based execution on a continuum. It's a very interesting paper. I definitely recommend you to read. And moves dependencies out of implicit model context into an explicit directed acyclic graph. The broader phrase graph of loops to me can include cycles as well. But adding more loops does not automatically create better grounding. Several loops can agree with one another while all optimizing the wrong proxy. A graph of loops therefore needs explicit arbitration when loops disagree, and one global budget across every branch and retry, independent counter metrics or audit checks, and hard anchors that the optimizing loops are not allowed to rewrite. This is closely related to Goodhart's effect. Once a measure becomes a target, pressure on that measure can weaken its relationships with the real objective. Graphs also create more possible feedback paths. If a path can repeatedly reach model calls, tools, handoffs, or state growing operations. Without a real bound, the system may never terminate. A 2026 empirical study calls these failures infinite agentic loops and analyzes them through an agentic loop dependence graph. I will therefore treat a graph of loops as an important orchestration architecture, but not as a replacement for loop engineering and not as a universally recognized basic loop type. That's just my opinion. The loop performs the feedback-driven work to me, and the graph makes dependencies and parallelisms, arbitration, and global control explicit. We can map the broader design space with a few questions. For example, who controls the next step? The model, the program, a hybrid, a verifier, a reviewer, an agent, a human, or maybe another agent. What shape does the system have? Is it a linear cycle, a state machine, nested loops, branching search, parallel candidates, a hierarchy, or an event-driven outer loop? What feedback enters the system? Is it tool observations, compiler errors, test failures, static analysis results, performance measurements, model criticism, human review, or production data? Where does memory live? In the conversation, a scratchpad, files, Obsidian, a database, for example, Git history, an issue tracker, or curated lessons. And what is being improved? The answer, the plan, the code, the patch, the memory, the harness, or the operating process. And what stops the system? Is it verified success, no work, a step limit, maybe cost limit? Is it lack of progress, an action that is considered unsafe, human escalation, or external cancellation? So every loop family in this episode is one useful combination of those choices. Other combinations are also possible, but the goal is not to memorize a supposedly a complete list. That's not my intention. The goal is to understand the design variables well enough to build and evaluate new systems scientifically. So let's continue with, next step, which is about the project that you're gonna use. Alright, so in this chapter, I'll go through the project for the continuation of this episode, and my intention is to talk about or present one single example and go through it from different architectural perspectives, different loop architectures. So instead of having like 30 different examples, which is going to be very hard to follow, one per architecture, we're just going to focus on just one example for the continuation of this part. So let's get started. Alright, it's exciting. We are going to become hands-on and talk about our project. However, before I start, I want to make the experiment crystal clear, because I don't want you to confuse this with an episode about creating a to-do app. This episode is about loop engineering, of course. The experiment that you're creating is for basically studying or understanding different loop architectures. So I want to clarify one thing. So loop engineering does not mean asking a model to keep generating code until an entire software product somehow appears. That's one of the use cases, but that's not what loop engineering is about. A loop can build a whole product, of course, but the important idea is the control process around each action. So the cycle we care about is observe the current state, decide what to do, take an action, receive feedback, verify what happened, and then either continue or change strategy or escalate or even completely stop. So I need a software problem that gives every loop architecture the same starting point and the same objective feedback. So the project we're gonna work on is a tiny Python code that basically is a tiny to-do API. It's a to-do list. A to-do has a title. It can be completed, no checkboxed, and it can also be archived. Okay, so the API lets us create to-dos and asks for statistics about active work. So the intentional bug we're gonna implement is gonna be very simple. The stats calculation gonna still count archive to-dos. Okay, so archive tasks are supposed to disappear from both the total count and completed count. So our failing example will contain 3 to-dos. One is going to be an active to do, but at the same time completed. So another one gonna be an active to do, but incomplete. And the third one gonna be completed and then archived. Okay. The correct statistic in this scenario is that we're supposed to have total 2 and complete 1, because 1 is archived. But the broken implementation returns total 3 and completed 2. Okay, that makes this a good loop engineering laboratory, in my opinion, because the agent has to inspect the repository, locate the implementation, understand the verifier, make a change, observe the result, and decide what happens next. So one loop architecture may let the model choose the next tool. Another may let Python force the phases. Another may use test failures to drive repair. Another may add, review, search multiple agents, spin up, or even a human approval. So we will study those based on this example. The important thing is that the software problem does not move underneath us. So same repository, same box, same verifier, but different control process. That's very important. In other words, the project stays fixed, but the loop changes. One more rule before we get started. I will create every dependency before I create a code that uses it. So if a function calls a helper, that helper will already exist. I do not want you to, discovering a missing function while you are doing this project with me. However, I'm gonna share the code with you so that you can just load this and start using it. Okay, now that the experiment and the implementation order are clear, I'm going to make some changes in my setup so that you can see both me and my screen. Okay, I put myself down here. I think it's safe here, not blocking anything. I'm also going to embed myself like this. Perfect. So you only see me and my mic. In order to create a new project, so my assumption is that you are using PyCharm. So I am using PyCharm, so I expect you to use PyCharm too for this tutorial. But of course, you can choose to use something else. And also, I'm using Python 3.14 for this example. So in order to create a new project, you can either choose from the welcome screen, new, and then new project, or if you already have a project open, from file, new project. Both works. So you do new project, and I'm here gonna use pure Python here because the interesting complexity in this episode is, the agentic loops, not the application framework. So bear with me. We're gonna just use pure Python. It's a simple project. We're not gonna use any framework. Also, it makes things complex if I use an existing framework because you need to be familiar with it, and you may not be able to follow if you are not familiar. It just increases the duration of this tutorial. So pure Python, I'm gonna name this project to do underscore project. And I am keeping an isolated project environment with 3.14. I'm leaving Git creation off for the moment because I want to create a baseline commit myself after we prove the bug exists. Also, I keep it disabled, the create welcome script disabled. All right, I press create. So the expectation is in the project explorer here, you should not see any file. If you see a main.py or any other file, just remove them. Only file folder you have to see is .vmf, which is your virtual environment. So before I start implementing, I open the PyCharm's terminal to check a few things. One is the Python version, to make sure this is correct version, 3.14. And I also want to make sure that you are using the environment, virtual environment, which is correct. It's to do project, VM, etc. All right. So I am going to now install some dependencies because that's what we need to do. So I am going to use FastAPI for the tiny HTTP API and HTTPX because FastAPI's test client uses it. And of course, we're gonna use a PyTest because tests will become one of our strongest verifiers in our loops. So we need to have loops. So if I run import FastAPI HTTPX PyTest print dependencies, okay, my expectation is that I get an error saying no module FastAPI or HTTPX. So we have to install it. In order to install it, it's python-m pipe install FastAPI space HTTPX space PyTest. As simple as that. If I run the previous command again, it will say dependencies okay. Perfect. Now, I'm going to create our first file, which is the models.py. So basically this file exists for one reason. I want the shape of a to-do item to be explicit and separate from storage and API behavior. That's why I created models.py. So I'm going to minimize this, and here I'm going to create a data class. And you may ask why I'm creating a data class, because it gives us a small data object without writing a custom constructor. So every to-do we're going to create as a ID, int, a title of a type string, a completed status flag, boolean, and as you can guess, archived as boolean. And these are gonna have a default value of false to begin with. And yeah, these two flags actually are extremely important because the bug that we're gonna later on introduce intentionally comes from treating completed and archived as if they were independent, when the statistics should exclude archived items entirely. It doesn't, so that's very important. The next thing, I'm going to create another file, which is store.py. So this file, I'm going to create it piece by piece. Basically, it's going to give the application one place to that one place that owns an in-memory database, basically, or collection, and also keep track of the numeric ID of these to-dos. All right, so we're gonna have a first thing first. We have to import the model we created to do, and we're gonna create a class to do store. This class needs an, of course, constructor, which gonna return nothing for now. So this is, we need a temporary in-memory database. So it's gonna be self to-dos of type list to do, which is gonna be empty in the beginning, and then a next ID of type int, which is gonna start from number 1. So this next ID counter makes newly created to-dos predictable, which also makes the test deterministic. This is very important feature we have to keep in mind when designing a system, to make sure tests are deterministic and predictable. Now, next thing, I need to create another function called clear function. This function is very important because it mainly exists for, in this case, for the test isolation. So every test needs a way for reset, so that, by reset I mean resetting both the to-do list and also the next ID. So then one test then doesn't contaminate another test. That's very important to keep them isolated. So we need a clear function to do that. So self none, and we do self to-dos clear, and self next ID 1. Very simple. So resetting both pieces of state is important because, then we make sure the tests are not depend on the execution order. Next thing I'm gonna do is naturally create to-do list, which is gonna be getting a title of type string and return a to-do after creation. So we have to create a to-do. We call the constructor, and you may ask, when did we create this constructor? We didn't, because it's a data class. That's one of the usefulness of data classes. And we're gonna append this newly created to-dos like this to the to-dos list, and we're gonna increase next ID by 1, which means we now added 1 more. All right, is this error? Maybe I use PyCharm's import like this from models import to do. Right. Next thing, we're gonna create, 2 functions, archive, def archived, which receives a to-do ID. For now, you just put pass here, and complete again receives a to-do ID. But before I implement the body of these, I want to implement a helper function so that it's going to be used in these 2 functions. The helper function I'm going to create is going to be calling _find. It's a private function just for this class. So it gets a to-do ID, try to iterate over the existing list of existing to-dos, and then return that, find the ID, find the item, and then return it as an object. So for to-do in self to-dos, if to-do.id equals to to-do ID, it return to-do. As simple as that. Otherwise, it's supposed to raise a value error saying to-do does not exist. and to-do ID. As simple as that. So now that this helper exists, we can go to here and actually archive and complete, not archived and complete. So for archive, we can say, so to do equal to self. Let's find that to do ID, which is of type integer, and it's supposed to return the to do for us. Let's find that and set the flag archived to true and return it. As simple as that. For complete, same. We're gonna find that to do ID. Again, it's an int. Type returns to do and gets a to do ID. And it makes the completed true and return. Super simple. All right. Basically, we have everything. Now the important part is here, which is we're gonna introduce the buggy function, the intentionally buggy function, which is called stats function, which is supposed to return a dictionary of type string and int. So it returns a dictionary. The first item is total. The length is the length of to-dos, and completed is sum of. Now here's where we are introducing the bug. Sum of to do completed for to do in self to dos. And here it a comma. So this function produces the two numbers exposed by the stats endpoint, but I want to make sure that this works. So I am gonna create a test later on to, check the correct results and check the results of these stats with the expected one, with the correct one. But bear with me, for now, we need a few more things. The next thing we need, now that we have everything, is a new file called app.py. So this is the basically the HTTP layer that we're gonna have, and I deliberately keep it very thin. So the agent has to follow the call into, store.py and find the behavior in different files. So it's making it a little bit more complex. In order to do this, we first need to create an app, FastAPI, and with the help of PyCharm, we're gonna import it, FastAPI, and then a store, a to-do store. We create an object instance of to-do store, like this. And we create a class, create to-do request, base model, title, string. So this base model import from Pydantic. So basically this API owns the to-do store instance. So the request model says, says that creating a to-do requires a title, and Pydantic handles the request validation for us. That's very, very simple. So next I'm going to implement the post to-dos endpoint. So this endpoint exists only to translate an HTTP request into a store operation and then translate the to-do object back into a JSON friendly dictionary. but then we can't verify if it's correct with the test, as I said. So following the FastAPI convention, we create a decorator, app post to dos, def create to do. I expect that you're already familiar with this. So it basically says create a endpoint of type post, HTTP post, with this endpoint /to dos, and then we call a function name, and then this function is, of course, have a request create of type create to do request, which we defined here, and this is returning a dictionary. So here we have a to do. So this, because it's a post, it means that you have to create a to do. So it's a store.create request.title, and we return, a dictionary with ID, to do ID, title, to do.title, and the flag completed, do.completed, and archived. Okay, just reformatted it using PyCharm. Perfect. Just notice that ID assignment and to-do creation still belong to the store. So the endpoint is only an adapter around this behavior, nothing more than that. So now I'm going to implement the get endpoint for stats, and I want this endpoint to be almost empty because the visible API symptom should delegate to the deeper implementation where the real bug lives, which you already saw. So very simple, following FastAPI convention, app.get, it creates a get endpoint with /stats. So def get stats, this is supposed to return a dictionary string int, return store stats. As simple as that, one line. So this one line creates an important repository navigation problem. So the issue will mention the stats endpoint. You will see, you're gonna say the issue is with the stats endpoint, but the agent has to inspect the call path and discover that the calculation itself lives in store.py. Now, it's time to create our tests. So we create, first and foremost, we create a tests directory because I want executable evidence, not only model judgment. So I'm gonna create a new Python file called test_create to do.py. All right. Here, I am going to implement this test first. This is gonna be a correct test, a passing test, because it protects the behavior that already works and gives us a regression check, basically. So first I'm beginning with creating a client, test client app, but we want to use FastAPI test client. Also, this app is supposed to be coming from the app.py. And we need to, as a convention, we have to have a setup function, which basically returns nothing. But it clears the store. And the store is coming from the store that we created in the app. basically app and store, these two, FastAPI store. So here we using this real fast API test client means that it goes through the HTTP layer while still running locally and quickly. So it's kind of make FastAPI testable. It's pretty cool. Now I'm going to implement the creation test itself, which test create to do. Supposed to return nothing. So the response coming from client, and it's supposed to call to-dos, of course, and with the payload of type JSON, which PyCharm suggests this title by milk. Title by milk. So we have a response variable. We expect this response variable. So we create an assert. We expect this response variable have a status code 200. So it should work. It would be returning a correct code. Also, I think the PyCharm's AI predicts what I'm thinking correctly. It's supposed to return the right JSON with ID1, title by milk, because that's what I passed here, and 2 default values, completed, archive to false. So this verifies both HTTP status code and also the flags. Now, if we want to test if this works, we can simply open the PyCharm terminal, python-m pytest tests test-py-q. Object, no attribute ID. Let's see what we are missing here. Okay, I guess in store.py we probably here when we are creating, we have to return this to do. I think that's what we missed, I guess. Let's run this again. Yes, now it's passing. Perfect. So this basically gives us a baseline behavior that the agent is not allowed to regress from. Now I am creating another file for the testing the statistics, the one that's supposed to fail. And this test is the central verifier for the bug. So I'm going to implement it in several logical pieces. So first I'm going to basically create the file. I'm gonna name it test_stats.py. I'm gonna optimize this now. Similarly, I'm gonna create a client, test client, but PyCharm gets it incorrectly. It's supposed to be from FastAPI. This app supposed to come from app. Similarly, as per convention, we need to define a setup function that clears the store, and the store coming from the app again. So now we have no scenario at this moment. We have only the guaranteed isolation and the real HTTP client. Now I'm going to implement the first part of the test to create 3 to-dos. I want 3 because that lets us distinguish active completed work, active incomplete work, and archived work. So define def test archive to-dos are excluded from stats. Pretty long name, but it's okay. So I'm gonna remove this. So first one, we have to create, let's say, since we are writing an episode, step 1 is to do one is to write the episode Step 2 is to record the episode. And finally, the archived one gonna be create old task. Let's name it old task. So the second variable is intentionally not modified. It's not going to be modified later. It represents the active incomplete to do. That should still count towards total. So next I'm going to add the state changes. I will basically have to complete the first to do. So we just call the complete. First to do completed. The episode is now written. Now, and I'm gonna complete the last one, third one, the archived one. First and last now completed. And as expected, the last one supposed to be get archived. Right? That's what it's supposed to do. So after this, as you see, there are 3 stored objects, 3 objects basically, but only 2 of them are active. Exactly 1 active to do is completed. I'm going to call basically the stats endpoint. So I have to use this response client get stats, similar to the previous test. Similarly, I have to make sure the response is 200 that we are getting, which means the endpoint is supposed to exist. And we supposed to get a JSON, and total supposed to be 2 and completed supposed to be 1, because that's what we did. 2 completed, 1 is active. Basically, even though we have 2 completed, but 1 is archived, so it should not be counted towards the list of number of completed. So it should be actually 1 completed, and in total we should have only 2, to-dos. All right. In order to test this, Python-mpy test. This runs the entire tests. 1 passed and 1 failed. And as you see, the expectation is that we get total 2 completed 1, but we get completed 2 and total 3, because it counts everything. Okay. This is exactly what we want. This is one reproducible, one known good behavior, and an objective verifier. So before the agent edits anything, I have to create a git ignore, so that since this file have caches, the interpreter environment, and also the PyCharm metadata, it will pollute the folder with a lot of unknown things that our agent gonna get confused. So it's a good practice that we have a git ignore and make sure we include folders and files that you don't need to be included in Git, so that also agent knows not to get them. So I'm gonna create a git ignore here. env. These are the environment folders. If they exist, is pretty standard. PyCache .pytest cache, which usually created by PyTest, and also the .idea that PyCharm creates. All right, now Next thing, I am gonna initialize a Git repository out of this. Git init, Git add, Git commit, a baseline, intentionally failing stat tests, and its status to see you have a clean working tree. So I'm gonna expand this project tree one more time to go through the files. We have a test folder with 2 files and 3 files in the root folder, app models.store. The issue we will give every loop architecture next is going to be deliberately short. And I'm putting it on a screen so that we can review together. I'm gonna create a scratch file here. So the issue that we're gonna provide to our agent in the upcoming chapter is gonna be the /stats endpoint correctly includes archive tasks. That's number 1. Archive tasks must not count toward total or completed, or the total or completed. That's the expected behavior. And preserve the current response structure. That's the one harness that you want to make sure that our agent is going to consider. And also all tests must pass. Notice that what the issue does not say, what this issue does not say, it does not tell the agent exactly to open store.py or does anything specific. It does not name the stats method. It does not give the correction. The agent has to locate the implementation, inspect the tests, form a hypothesis, edit the code, run the verifier, react to evidence, and decide when to stop. That's what you're gonna learn next with different loop architectures. The software problem stays fixed, as I said. What changes from this point onward is loop around the model. So now I'm going to create the smallest working boundary this baseline needs. I'm creating a file called llm.py, but first I need a callable and a small message type alias. So callable describes a function-like value. Message means one string to string dictionary, which is enough for fields such as role and content. Okay, so we're gonna create our first file, as I said, llm.py. I'm gonna minimize this. All right, so I'm gonna start with a message variable that is of type dictionary string. So now I'm implementing a LLM client class as a real class. The constructor of this class receives a complete function, which is the actual function that gets a model response. The complete method basically receives a list of messages and returns a string produced by that function. So I'm gonna start here by creating a class LLM client. I'm gonna remove these parts. It's a self, of course. And as I said, a complete function of type callable, which is, as I said, function. So this gonna have an array of list of messages and string. That's it. So this is gonna return none, and we have to import this callable as well. So from collections ABC, we import callable. So this is
setting a private attribute completed f function as completed function, and then we're gonna have another function called complete, which has a self, yes, and a list of messages. Yeah, and this is gonna return a string. So this returns the result of that callable function, and we're gonna pass these messages to this function. As simple as that. Very, very, very straightforward. So now I'm gonna implement the ask LLM function, which receives our client and one prompt. This wraps the prompt in a user message and calls complete. So let's do that. So we gonna define ask LLM as of type LLM client, and prompt string, and this is gonna return us a string. Actually, yeah, this is gonna have messages of we define variable messages of type list of messages, which gonna have role, which is user, and content prompt. This is supposed to be dictionary, and yeah, this is what we need. So as I said, we're gonna return this as we call this LLM attribute, we call the complete messages. So all right, so we already have a working LLM client in llm.py as we created. So the harness will reuse it. The harness adds the deterministic pieces around the model, basically repository tools, state, budgets, structured actions, and verification. So now I'm gonna create a new file called harness.py and adding its dependencies before basically any harness code uses them. So basically I need hashing, JSON, subprocess, time, and other things. You will see. So we're gonna create class repository tools, and here we're gonna do in itself, and we're gonna get root of type path. That returns, so the path needs to be imported from I guess it's this one, pathlib. And then we have to have a, so here we repository tools, we have a root, which is basically root.resolve, and we need another function called maybe safe path, that exists to stop a model supplied path from escaping the repository root. That's safe path. So this basically repository tools and safe path, this exists to put all repository access behind one control boundary. That's why we are doing this. And that's why we are creating safe path. So we create a target, self.root, and then provide, basically this requires a relative path that we get. I'm first creating this so that we don't end up with errors. So self root relative path, and then this will resolve. Hopefully it gets resolved. So if then we check if this target not equal to self root and self.root not in target.parents, it means basically path escapes repository. So we have to raise value error and we say path escapes repository and we return relative path. So this way we make sure this stays in the repository. So this is the harness we are creating. Return target. So with this, the important safety property is enforced by Python, not by a prompt. This is very important because the prompt that we are providing may do some crazy stuff, wants to break out, and we have to harness it. So a path that resolves outside the repository raises an error before any read or write happens. Next, I'm going to implement another function called list files. With this function, we provide a way for the agent to discover the repository before it can decide which file matters. But we do not want internal Git metadata mixed into that view. So files of list. So for path in self.root. Yeah, I think PyCharm is writing it correctly. So if path is file, we append it to the no, if it's a file, then continue. But if it's a git, if it's .git in path.parts, continue. Otherwise, just put an enter. Otherwise, we append string path relative to self.root. Yeah, so we need a path relative to the root folder, and then in the end we return, of course, with a new line. So we want new line in between them, so we join by sorted list of files. This says no overloads match this argument. Sorted files. Let me review. This is list of strings. Yeah, this is a list of strings because these are actually strings. And then for each path we do this. If not, yeah, of course we need one more rule here. No, if it's not file, continue. We don't want directories. If it's and if git is in this path, continue, and then we append. So this is correct now. So this method basically walks the repository and keeps only files, exclude.git, and converts to repository relative paths. Sort the list of files, and returns a deterministic text view. That's what it does. It's very useful for LLM to have this kind of deterministic list. Now I'm going to implement another function called read the file, right? So this gets a path. We need to basically get a safe path. We make sure the path is safe. That's the harness we implemented before. We make sure if not, if such target exists, if such target does not exist, then we return an error. File does not exist with the path. What is it saying? Explicit. Okay, yeah, we will get to the return part. And if not target is file, of course, that's another error. Error, not a file. In the end, if none of this happens, then we return the contents of the file, basically. So it resolves the path safely and returns explicit errors for missing paths or directories, and also reads the text only after those checks pass. Now you can, of course, you have to add other harnesses in a real production system, but like if it's safe, or we can skip some files that we don't want, which you already did, but maybe in a different way. But I'm just keeping it very, very, very simple. Now I'm going to implement another function for searching code. So listing files basically tells the agent that what exists, but searching let it locate a symbol such as, you know, stats function that we had, without operating every Python file manually. Sorry, without you know, opening every Python file manually. Search code, and we have to have a basically search query of type string, and this function is supposed to return a string. Also, this function is supposed to return string, and this function is supposed to, yeah, it is supposed to basically send the list, but in a string format, so it is still supposed to return a string. And safe path also supposed to, yeah, so it doesn't, yeah, it's supposed to return something of type path, because resolve returns something of type path, if I'm not mistaken. Yeah. We have a string query, so we have to have a list of matches, because it may be more than one match. So it's going to be list of strings of matches. So for basically each path in root, but then we have to limit it to the Python files in this case, for the sake of simplicity. So basically we get the contents of that file, path.readText, and then we do encoding with UTF-8. That's what PyCharm suggests. So for maybe we don't want to numerate over the lines. So line number and the line itself in an enumeratable of this content dot, maybe we want to have split lines, start equals to 1. Maybe. So basically this is iterating from line 1 and returns the line number and the line itself. So if query, we make sure we turn it into lowercase in line.lower, even though In Python, things are case sensitive, but maybe for now we just search, because just a search is a case insensitive search. If query.lower in we get the relative path of relative to self.root. We want to get the relative path. It's already a match, so we already get the match, so we get the relative path. So we basically have to now append it to this list of matches. So we append it as a string. So we get relative path, the line number, and the line. How about that? And eventually, after we get everything, we return it. We can return, why not, with a new line. We are going with the suggestion. Yeah, but if there is no result, if this is empty, it's going to just be an empty lines. Maybe it's better, for the sake of the better prompt, we wrap it with or no matches found, or no matches, simply. Yeah, isn't it better? And also, I think, yeah, I think this is fine. I think maybe just the first 100, just to give it a limit. All right. I'm gonna maybe format it. There is an here explicit return. Or this is supposed to be here. Tab. Yeah, perfect. So this result now includes the relative file name, the line number, and matching line. This gives the model a compact evidence it can use to decide what to inspect next. Now I'm going to implement another function called, if you can guess, now we had search, we had read file, we had list file. So it's time for another function called write file. So this function exists to give these our agents a control edit capability while protecting harness files that should not be self-modified during an ordinary coding task. So I'm gonna give it a write file, this agent, I mean, and then hate it when PyCharm can't figure out the indentions. Path string, content string, and returns a string. Just what's wrong? Itself gets a path. Oh, it's extra. Right, perfect. Oh. Okay, perfect. So we want to write this content into this path. In order to do that, we have to first make sure this is safe, as you can guess. So we make sure this is a safe path. So we get the target then, and then the ones that are protected not to be touched, and this is very important, we create a list of protected files that we want to make sure agent cannot touch. It's harness.py, and soon we're gonna have something very interesting. I'm just gonna add it here. We'll see what's that. A JSON, config JSON, .agent config JSON. But we will talk about it later. So protected. All right. So if path in protected, what should happen? If the path that the agent wants to write is in the list of protected files, we say what? We said, oops, error, protected file, this path. Otherwise, of course, the target, then if it's like in a subfolder or whatever, it has to create a folder, mkdir, and then provide the parents and exist okay true. So checks if it exists and then creates the parents. If it happens, then we have to think it should. Oh, it should start writing the text, and then we just make sure to follow in writing coding. TF8. Oops. Perfect. So we return then successful or wrote into this path. Okay, I think this is fine. The write still goes through safe path here, rejects protection paths, create the parent directory only when needed, writes this UTF-8 text here, and returns a simple confirmation string wrote to this path. Now I'm going to implement run tests. I want verification to be controlled by the runtime, so the model does not get to invent which command counts to proof of success. So we gonna create another function called run tests, which returns a dictionary of string, and for now I'm gonna keep it any. So results equal to subprocess run. So we need subprocess because basically it's a Python command we want to run. So this Python file is going to run under a Python command. So we want to do it with the subprocess. It lets us to create a process from this process. We're going to call another Python file here. So the command should start with, of course, this requires an array. So each part of this array, you can think of a command line command that each part of this array is one token of this command line. For example, the first part is we want to run a Python command, so it's going to be Python, and then the second part we're going to comma, it's a second index of this array. So we do -m, and then we call PyTest. We want to run a test, and then -q. It's a normal PyTest command. Then our current working directory is self.root. Our basically capture output. We want to capture the output. Let's see what else coming. Text equals to true. What else? And maybe a timeout. Gonna help. 2 minutes. So yeah, we get this result, and then we return the result. So the result includes the basically exit code, so that we know whether it's an error or command is successful, so the agent knows that. So it's going to be as PyCharm suggests, result.return code, because this sub process returns a return code, so we just returns that. So std out and std error in case it exists. So std out gonna be the results std out, but maybe not everything, maybe just first, I don't know, 8,000 characters, and std error results maybe 4,000 characters for now, just for the sake of simplicity. Can be adjusted later. All right, so as you see here, our harness.py now runs the same PyTest command in the repository root that captures output and applies a timeout and returns structured exit code, std out and std error. That makes the test evidence machine checkable. The agent can check that. Now I'm going to implement another function called git diff. It helps the harness and reviewers can inspect exactly what changed relative to our committed baseline. So I think what PyCharm suggested is kind of correct. Git diff, just that we have to also mention here in this current folder, this root text true, capture output true. I think a timeout is also makes sense here, 30 seconds. Perfect. And then it returns that result.std out. If there is nothing, I think we can just say no changes. As simple as that. So because we committed intentionally broken started state, this diff now isolates only the agent's modification. If nothing changed, the method returns the no changes. Now I'm going to implement another function, which is very interesting. I'm calling it fingerprint. So I need a way to detect whether repeated loop iterations are producing the exact same repository change. So I need to fingerprint this process, this payload. So I call it fingerprint for the agent. And this is going to return a string. I'm going to call it payload. This variable, which payload is the this result of this function, git diff dot. I'm going to encode it UTF-8. So we return the. We can return the payload like this, but better to use a hash function here, so that with the hash function it's the best way, because if it's the same output, it's gonna return the same hash. We don't need to return the exact entire string. It's gonna be too much. Also use a lot of tokens. So with the hash lib, we can do the payload and hex digest. But then we have to import this hash lib. Yes, perfect. Perfect. So this function basically hashes the current git diff. If several recent fingerprints are identical, the loop can now recognize, stagnation instead of spending the entire budget, repeating the same state. This is very important in an actual loop engineering system. So now I'm going to implement, you can guess, now it's time to execute. So we need an execution function, like any loop system. So execute. What we want to execute? We want to execute some name, string, and some arguments of type dictionary. And right now I'm gonna get an any, and this is gonna return any. All right, so we don't want to let the agent execute everything, right? We want the agent to execute things that we want it to execute. So I'm gonna see if the PyCharm can figure out what I'm gonna write. So I'm gonna say if name equals to so I'm gonna probably say the name of these functions. So list files. So it's gonna return self list files. See, it just fills it. Else if name read file, return read file, write file, run test, git. Else if name equals to git diff, yeah, it return self git diff. That's it. Otherwise, if none of these, if agent comes with a different thing to execute that is not in this list, we should say raise value error. A good message would be unknown tool or unknown name, but unknown tool is better because they're tool for the AI agent to me. Yeah, that's it. Yeah, that's great. So there is no dynamic arbitrary command execution here. It's just known names are dispatched explicitly and an unknown tool name raises an error. This keeps the action surface inspectable. Now I'm going to implement I'm gonna name it for now terminal status, and I'm gonna give it a list of, bear with me here I need to implement a vocabulary basically. So an actual production loop, trying to organize my mind. So an actual production loop needs more than success or failure. So I want the runtime to distinguish blocked versus stalled versus unsafe versus exhausted versus human escalation, and yeah, no operation probably. So I'm gonna name this terminal status to a bunch of literals. I'm gonna import this typing. So it can be running. Status could be running. Status could be success. Status could be blocked. Status could be, I call it no operation. I call next could be unsafe. If it is unsafe, needs human. Like if it needs a human escalation. Exhausted, and probably stalled if it's timed out. Yeah, maybe for now these are okay. What is it? Oh, this one. Exhausted with an A. All right, perfect. So these names basically make stopping behavior explicit. So later, the loop can record white stop instead of collapsing every non-success case into, one value error. We will see. Now I'm going to implement another class, data class this time, called maybe data class. I'm calling it run state. This object exists so the loop has one inspectable place for its goals. And not only goals, but also current status, iteration count, conversational messages, observation, memories, fingerprints, usage counters, which translates into the cost, and start time. So this is a loop run state basically. So we call it like a goal. It has a goal of type string. It has a status of type, you can guess, terminal status. It has a iteration, which starts from iteration number 0. It has a list of messages, which basically is a dictionary of string and string. So this is like a field with default factory list. So I'm gonna import fields from data class. And we want to have a list of observations, which is a list of dictionaries, and then this is also a field with default factory list. And memories, this is very important, memories. Any loop has memories. So this is a list of string. Yeah, this is also a list of, no, this memories are list of strings only, basically. And yeah, this is correct. So maybe some other stuff like tool calls, which is number of calls, and model calls, number of calls to the model, number of calls to the tools, the other one, and also a start to that, so that we know when this is started, of type time but monotonic. Import time. All right, like this. Yeah, perfect. Okay, so the important idea here is that state belongs to the harness, not only to the model's hidden context. That lets deterministic code enforce budgets, record evidence, and also inspect the progress. In a real production system, these are more structured than in one harness.py file, but just for the sake of simplicity, I'm just making it super simple for this episode. So now I'm going to implement another class called another data class called budget, because we don't want this to go forever, right? We want to measure the budget. So we want to provide the maximum model calls possible. I think maybe 30 is fine for a simple loop. Maximum times that agent can call tools is maybe double the number of times it can call the model, and maximum seconds it can run is maybe just to start with 600, so that 10 minutes, so that we know doesn't go forever. And of course it's a budget, so we have to have a check function. If that basically gets the state of run state. I just remove this. So the elapsed time is time monotonic minus when it's been started is the elapsed seconds. If state.model calls greater than max model or greater or equal to greater max model calls, we basically it's an error, raise runtime error, and we return something like model call exceeded budget. No, model call budget exhausted. Budget is done. If state tool calls greater than this, tool call budget exhausted. If elapsed time greater than maximum seconds, then time budget exhausted. So we have three types of budgets. Yeah, I think otherwise it's fine. It returns nothing, it passes. Perfect. So again, this check method measures current usage and raises as soon as any limit is reached. Later on, you will see that before continuing, we call this, so stopping is enforced outside the model. So now I'm going to implement another, of course, these are three actions. So we need to have action types, basically, which is also literal. So it's either run tool, write file. No, it's actually tool. We are using tool. And then we have to know when to stop. So there should be a finish. And another action is gonna be blocked. It can be that it's blocked. So a data class of action that has a type of action type, and yeah, these are needed. So it has a name of type string. So it can also be none, sure. And arguments of type dictionary that it has it's field default factory dictionary, and a summary of this action, maybe summary string none equals to none, and also the reason of this action. Why are we doing this action? Okay, that's the program here. Oh, it's frozen equals to true. It's here. It's a typo, class action. Okay. So perfect. So the structured fields separate the action type, tool name, and the arguments that we're gonna use with this action. Also the operational reason and the summary. This is much safer to validate than treating arbitrary natural language output as executable intent. Now I'm going to implement the first part of parse action, and this function that I'm gonna create is because model output is unstructured text until the runtime successfully parses it as JSON and reads the requested action type. So I'm gonna do a def parse action that gets a basically raw string and then returns an action. So we get a raw JSON, and the action type is gonna be reading data type, and yeah, it's gonna, this first part converts the raw string to JSON and extracts the type field, and nothing executes this. You are only turning text into data, and runtime can validate. Now I'm gonna basically implement the allowed type check, because it can be something that is not allowed. So I want invalid action types to fail immediately instead of failing through into unpredictable behavior. So if action type that we're gonna get is not in list of these three, tool finish blocked, it basically raise invalid action type. So we can also put this action type, something like this. Now I'm going to implement tool action branch, where this part exists to validate that a tool request actually names a tool and its arguments are a dictionary before creating an action object. So I'm gonna do if action type equals to tool, name equals to data get name. If this is not an instance of name, so raise value invalid tool name or invalid, no, this is gonna be tool action requires a name. Yeah, that's better. So arguments equals to data.get arguments, otherwise empty. So if not instance of arguments, return tool action. Tool arguments must be an object. These are the usual checks. And then we return action type, name, and argument. Perfect. So this is preventing malformed JSON from reaching the tool dispatcher. So the runtime now has a typed tool name, structured arguments, and an optional short reason. Now I'm going to implement the final branch, a finish request. So a finish request is different from verified success. So this branch only records the model's completion request and summary. So I'm gonna do if action type finish, then we return action of type finish, or action type, same thing. Summary, we get a summary from the data. Otherwise, if none of this happens, we set the type to blocked. Or it doesn't need else, just none of this happens, then it's automatically blocked. So with this, the parser now covers every allowed action shape. So it validates the structure, but it still does not decide whether a requested action is safe or successful. That happens in higher layers. Finally, I'm going to implement the harness data class. So this is data class, harness, is LLM client, and it gets a list of tools. Basically, it gets the budget, it gets the, yeah, that's all. That's all it gets. The state is not a part of this. So at this point, we have, yeah, I guess that's all. I think that's it. At this point, we have this infrastructure, but we still do not have an agent. The loop is what will repeatedly combine model decisions with these tools, state, and stopping rules. So this is our baseline. Next chapter, which I'm going to start right after, is we're going to create our first loop. Let's continue. Okay, so this is getting exciting. So we're going to create our very first loop. This loop gives the model control over the next action. This is the very basic loop that we're going to create and close this episode with. In the upcoming episode, next episode, part 2 of loop engineering episode that's gonna come very soon, right after this, we're gonna work or implement or discuss about other types of loops. This is the first loop, we call it loop 1, and this is commonly known as model controlled loop, model controlled tool loop, where a model uses a bunch of control tools. And continue. Basically, the cycle is the loop is gonna, the agent is gonna observe, choose a tool, act, observe the result, and repeat. So the model may list files. We already have a function, search for a symbol, read a test, edit a file, which already created everything, all these tools, run the tests. We have a tool for it. Inspect the diff, we created a tool for that, request completion, or report that it is blocked. We have everything. The agent will gonna have all the tools that we created for it. So this cycle resembles the reasoning and action structure introduced by a paper that I was reading called React, which interleaves model reasoning with actions and environmental observations. For software work, the interface itself matters. SUI agent demonstrated that a custom agent computer interface can strongly affect how well an agent navigates a repository, edits file, and execute programs. So the system instruction tells the model to solve the issue with the simplest save change. So it lists the available tools, requires exactly one JSON action per response, and defines the schemas for tool use. And also understand when to complete, and also understand when the system is blocked. It also requires the agent to inspect relevant code and tests, avoid weakening tests, and prefer focus change and never claim success without verification. So it only knows if something is successful, if some action is successful, if the evidence is there. The runtime starts with the system instruction and the issue. On every step, it checks the global budget and calls the model. We already have the class for the budget, and we already have the class for the actions. So if the model returns invalid JSON, the runtime does not guess. It sends back the validation error and asks for a one valid action, basically. So if the model reports that it is blocked, the loop ends in that block state. And if the model requests completion, the runtime runs the tests independently. So a passing test command allows the success state, And a failing test command rejects the completion request and returns the evidence to the model. For a tool action, the runtime validates the tool name and its arguments, execute the operation, record the result, and adds the observation to the conversation. After each action, the loop fingerprints the Git diff. We already have a fingerprint function. If the system fingerprint appears repeatedly, the system decides that the run has stalled instead of burning the entire budget. So the design is this. The trigger is a user supplied issue. The control is the model. The actions are repository tools. And the feedback is the tool output and test evidence. Okay. You may think of the state. The state is the conversation plus the explicit run state. So the verifier is the fixed test command. We already have some tests. The loop stops on verified success, a blocked condition, stagnation, or budget exhaustion. And we already have all these checks. We created it. The architecture is super simple, yet very flexible. The model can basically adapt to an unfamiliar repository. So any repository that you attach to this is supposed to work. But the control flow is probabilistic. It may repeat actions, forget to test, or request completion too early. That leads naturally to the opposite design. Before I implement the first loop, I am creating a new file called loops.py. Everything in this file will depend on the harness you already created. So the first thing I am going to do is add these dependencies explicitly. You will see. Let's start. I'm going to basically start by creating a new file called loops.py. And in this one, I'm gonna implement the first part of the system instruction. This part defines the basically agent's role, its goal, and the exact tools that it is allowed to request. So I'm going to do a model underscore loop underscore system. It's basically a prompt, kinda. So you are a software engineering agent. Solve the assigned issue with the smallest safe change. We have to specify the tools that we created in the previous chapter. So available tools include. We're gonna one by one basically copy this. List files, read files, search code, write files, run tests, Git diff. Yeah, so yeah, I think this is fine. So the tool list is part of the contract between model and harness. So we created a contract now, and the model can now reason about these names, but it cannot invent an arbitrary shell commands because the dispatcher only implements this fixed surface. In case it hallucinates and does that, we should have a good harness to prevent running a hallucinated action or an action that is not defined. So that's why harness is very important, because models can anyway hallucinate. Now I'm going to implement the structured response formats. I need predictable JSON shape for tool actions. So also for finish requests and also for the blocked report. So parse action that we created in the previous chapter can validate every model response. So I think we should continue here. We should continue saying, so it should return exactly one JSON object per response. Tool action, we should not explain to the model what is the structure of the tool action. So it's supposed to have a type, if you remember, which is the tool. It's supposed to have a name, is tool name. This is a tool action. Remember, we had 3 actions: tool, completion request, the tool finish, and blocked. So this is the tool one. The tool has type, name, if you remember. Arguments, which is a object, and reason, which is a short operational reason. Now we also have a completion request, which is another type. Type is, if you remember, was finish. Summary was basically what changed. And we have blocked request, which is type blocked. Reason is why safe progress is impossible. Yeah, I think this is fine. This is a good boundary. So this boundary between probabilistic language generation and deterministic control flow is quite important because the model chooses among structured options. Python decides what those options actually do. Okay, so agent model basically decides something, but then it's the Python that actually decides if those what those options actually do. We don't let the agent decides that. We have to program that. So that's the harness we have to build. Finally, I'm going to implement the operating rules, and these rules tell the model to inspect before editing and respect tests, keep changes focused, and never claim success without verification. So we now add some rules here. The rules are basically inspect relevant code before editing, inspect tests before editing, do not modify tests merely to hide a defect. Many problems in productions because you don't have this rule. Because many times I've seen in production that you ask agent to go and fix a problem, and instead of that agent goes and fix the problem, it fixes a test. So this is a very important harness to implement. You prefer focused changes over exhaustive, nonsense, and do not claim success without verification. And PyCharm suggests something, but I want to be precise. Also provide only a short action reason, not a private reasoning. Many of you may think this is too much for harness, but in my opinion, these are the minimum that you can implement. I think if you want to make sure that your agent is doing correctly, it's better that you add some harness. Don't let agent decides for you. That's the whole point. So these prompt rules are very important guidance, but they are not our only protection. So the harness will still enforce repository boundaries, budgets, and final verification in code. Now I'm going to implement the function signature and initial run state first. So the function receives the harness, the issue, and the hard step limit, because one model control trajectory still needs a deterministic outer boundary. So we do a def model controlled loop. Basically, we define a function called model controlled loop. This function gonna have some arguments. As I said, it's gonna have the harness of type harness. It's gonna have the issue of type string and the maximum steps, which we gave it 20. And this is gonna return a run state. So we import this, of course. Perfect. So the state is the object of type run state. The goal is the issue. And creating run state immediately gives every later action a place to record status, usage, observation, and progress, because that's what this run state does. Next, I'm going to implement the initial message list, of course, and the model starts with the system contract and user's issue, and later tool results will be appended to this same conversation. So state.messages equal role system content. So it's a role is the system, of course, because the system that is doing this, and the content is this function that we created, model loop system. This prompt. This is the first message. And we need another message, which is coming from the user. What user wants is the issue. That's usually the case. You need to have a system message and a user message. That's how usually the LLM agents work. LLM APIs work, basically. All right. So this message list is the model's working context for one run. So the harness still keeps separate runtime state outside that context. Now I'm going to implement the bounded step loop and budget check. This exists, so the model may choose the next action, but it cannot choose to run forever because we have a budget. So for each step in the range between 1 and maximum step that is being provided plus 1, we basically set the state's iteration, because if you remember, we had an iteration to this step number. We try to check the budget, so it will be this harness dot budget dot check, and then giving the state. So if there is an error, it's gonna be error of type runtime. The state dot status will be budget exhausted, right? So status will be exhausted. If you remember, we had exhausted here. So the state will be exhausted. And the state's observation, we add an observation to the state that the observation will be an error of STRE. Basically, it's an object that we are appending here. Yes. And do we return? We return the state. Yeah, as simple as that. Yeah, basically at every iteration, Python updates the step number and takes the global budget, whether continuing is still allowed or not. The runtime records the observations, as simple as that. And also, if it's exhausted, then it stops. So next, I'm going to basically implement the actual model call and increment the model call counter. This is probabilistic decision point for the loop. So it's gonna be basically harness.llm.complete state.messages and state.model calls +1. Yeah, I think this is fine. Model calls, yeah, we did the model call, so it increased by 1. So it's only a proposal, of course. So the next code will parse and validate it before any tool action can happen. So I have to implement action parsing and invalid response recovery path. Models sometimes return malformed output, so robust loops needs a way to reject that type of output and ask again without crashing the entire run. So I need to continue by a try. So we do an action equal a parse action, which, if you remember, we implemented in the previous chapter. Which action? This action, but I think we have to first assign this to a variable. We call it raw for now, and then we parse to raw. We pass the raw to this parse action. If you look at the parse action one more time, this basically raise value errors in different instances. So we need to accept these value errors, value error, and JSON decode error, because it may be a JSON decode error. Import this name from JSON. So in that case, it will be state dot messages append. So we have to append an object, say role user. Content is gonna be basically your response was invalid. Return one valid JSON action, and also pass the error that we received. Yeah, I think that's fine. And continue, basically. So if parsing fails, the error becomes new feedback in the conversation, and the loop continues to the next bounded step. Now I'm going to implement the blocked branch. So this exists so the model can explicitly report that safe progress is not possible. So instead of pretending it finishes or repeatedly attempting the same unsafe action. So we need to have a check for that. All right, so now this outside of this try catch, we say if action type is is blocked. So we set the status to blocked, and we append this to an observation that the action was the action, of course, and we return it. That's as simple as that. We don't need too much stuff. So basically, blocked becomes a real terminal state with the requested action recorded in observations for later inspection. Now I'm going to implement, you can guess, the finish branch. So this is one of the most important pieces. A model saying finish does not create success. So this is one of the most important pieces. A model saying finish does not create success. That's very important. So the runtime runs the test itself. So it's gonna be if action.type equals to finish. Basically, we have to have a verification equal to harness.tools.runTests. Now we call this runTests function that basically run the PyTest. Now we use the tool. So it means tool calls increase by 1. Of course, in a real production, we can abstract this. So we run this through maybe we pass this state to this verification so that it does it automatically. But now, for the sake of simplicity, I'm doing it right here. So we increase tool calls by 1. So state observation dot append. It's a new observation depending on the result. So the finish underscore request will be this action. The verification will be this verification here. If verification exit code, it returns the exit code, equals to 0, it means the status of the state is success, and it returns state. It means the test is successful. All right, if it's 0, so it just return the state. So no further action is required. This function is finished. Otherwise, it means the test has been failed. So we have to basically create a new message. We append a new message from with the role assistant, which includes the content raw, this one from the harness, and messages. And we also add another message with role user saying that completion was rejected because test failed. And we continue by saying the content is actually like this, but continue by saying the tests failed, and of course we need to provide plus json.dumps the verification that we created here, run test, the result of the tests, plus we close this parenthesis, and then we continue until the budget gets exhausted. So if basically, if test pass, Python assigns success. If they fail, the finish request is rejected. The failure evidence is appended to the conversation, and the model gets another chance within the remaining budget. Now, I'm going to implement ordinary tool execution. A validated tool action is dispatched through repository tools, and any tool exception is converted into unstructured feedback instead of terminating the process unexpectedly. Yeah, outside of this, if we assert action.name is not none, we try result equals to harness.tools.execute. So now we have to execute the action. Which action? The action.name with the actions arguments. And because this execute function raise a value error, but then each of these gonna raise different types of errors, so it's gonna be more of a general exception. So except exception, the result will be error, and then we have to basically create a string. So the string will be type error, type of the error, the name of the error, basically that, and the actual error, the error type of the. Yeah, so I think this makes sense. And because we are now call the tool, it means we have to increase number of the times we use the tools by 1. So this keeps tool failure inside the observation loop, and the model can see the error on the next step and decide how to respond. Now we need another thing. I'm going to implement the observation and conversation updates. This part exists to both the runtime log and the model context receive the results of the action that just happened, basically. So I'm going to create this state.observations, and I'm going to append the action and result. What is this about this here? And I'm gonna do the state.messages append the role assistant and content raw. Perfect. And I am going to add another message with the role user, and content is going to be basically the tool result, like this, to stand out. Sometimes you have to capitalize for the LLM to stand out. Plus json.dumps, and here you put the result with indentation. That's it. Oh, this is like this. All right. Tools calls is tool calls, not tools calls. Tool calls. Okay, perfect. Okay. So with this, we have now. Oh, one more thing. Here that we did this indentation, I think. We need one more thing here. So indent 2, and then we need to add a default here. So default is gonna be of type string. Yeah, all right, perfect. So the runtime keeps the structured action and result for traceability. So the model receives a JSON formatted tool result. It can use it for the next decision. Next, I am going to implement the stagnation detection. So I hash the current diff after each tool cycle and compare the most recent fingerprints, because a loop can consume the entire budget without making any new progress. So that's why we implemented the fingerprint, if you remember. So we're gonna create a fingerprint, which we're gonna then call the fingerprint function that we introduced. And state.fingerprints.append fingerprint. So the run state is supposed to have I think I missed adding fingerprints here. Yeah. All right. And the recent equals to state.fingerprints is, and if length recent equals to 4 and length set recent equals to 1, return dot status equals to stalled return state. So basically state, that's the return state. Basically, if 4 recent fingerprints are identical, that's what it says, the runtime marks the run stalled and stops. This is a concrete no progress detector rather than asking the model whether it feels stuck. Finally, if it happens, I'm going to implement the step limit exit. So if the loop reaches the maximum number of steps without another terminal condition, Python makes it exhausted. State.status equals exhausted return state. Always forget the A. All right. So now this loop has explicit success. Where is it? Here. This loop has explicit success, explicit blocked, and exhausted outcomes plus protected test verification. That is the point where the one-shot model has becomes a control operating process. Now I am going to run this loop so that you can see what's the result. All right, now I want to run the system we just built against the intentionally broken to-do repository that we built a couple of chapters before. So the loop code stays provider neutral. So this next file is only the adapter for today's chapter, today's episode. First, I'm installing the OpenAI Python SDK. This is the only new package we need for the live model call. And then I'm gonna basically continue creating the OpenAI Adapter.py for actually using OpenAI ChatGPT API. All right, so I'm gonna use this this terminal, PyCharm's terminal. So I'm gonna write python -m pipe install OpenAI. This is installing OpenAI package in this repository. Now I'm gonna create a new file called OpenAI Adapter, because we created it provider neutral. Adapter.py. So this adapter reads the model name from OpenAI model and OpenAI API key from the environment, sends our message list to the response API and gives LLM client to the return text. So we basically start by importing OpenAI, of course, and then defining a new function, create OpenAI LLM, which returns LLM client. And we create a client equals OpenAI, model equals os dot environment variable OpenAI model. Of course, os we have to import, and we have to define complete, because if you remember, it was a callable. Now we have to define that, which requires messages as a list of basically message, which we have to import here. If you remember, we had a message dictionary string. And this is gonna return a string. So response gonna be client.responses.create. If you're familiar with OpenAI SDK, this is how we're gonna create a basically client responses object. So it's gonna be model, and input gonna be the messages. Okay, so return response dot output text. All right, let's see how it works. So they eventually we're gonna return the LLM client object. We have to create a new LLM client and then provide this complete function as a callable. That's it. So only this adapter knows which SDK is underneath. The harness.py and loops.py do not change. That's the beauty of this architecture. Now I'm gonna create another file called, let's call it run loop1.py. And I'm gonna create the issue. We have to create the issue, right? This is the issue here. What was the issue? If you remember, it was the stats endpoint. And the stats endpoint incorrectly. So basically I have this scratch file. So yeah, I just copy paste that here. The stats endpoint incorrectly includes archive tasks. Archive tasks must not count toward the total or completed. Preserve the current response structure. All tests must pass. If you remember, we created this prompt. Now I'm implementing the main. It treats the project directory as the repository root and creates the real model client, architecture, and creates the tools and budget and runs our loop 1 that we created. Also prints the state, final tests, and final git diff. So we're gonna create the main function here that returns nothing. The root is gonna be the root of this file, current file, parent. We have to, of course, import the path, which is from pathlib. And we have to create the harness. The harness gonna be needing LLM, which we're gonna create this OpenAI LLM. Let's review. It has an LLM as of type LLM client, tools, and budget. So LLM is this create OpenAI LLM that we just created, and tools gonna be repository tools root, and budget is gonna be budget, and of course we have to import budget. The max here we can pretty much customize this. Max model calls, max tool calls, we can say 40, and max seconds, we can say 305 minutes basically. Yeah, that's it. And this is going to be our harness. We also need a state, which from model control loop, we provide this harness that we created and the issue and the max steps. We can say 20, for example. Also, we can create print status. We can print, for example, iterations, state iteration. We can print model calls, state model calls, and print tool calls. So how many times the tool has been called. And we can print also, final tests, which is going to be print harness.tools.run tests. We can create final diff, which prints off the final difference, basically final changes, which is harness.tools.getDiff. We can, I think that's it. And finally, I'm adding the normal Python entry point, and that's actually gonna call the main. So if underscore score name, we call the main. That's it. The runner is complete. But of course, before I let the agent change anything, I want to prove the starting state is still broken. So let's test that. That initial state is still broken. If you remember, if you were running PyTest, there were 1 failed. The total is 3, completed 2. Expected is total 2, completed 1, if you remember. I have to add the OpenAI API key in my shell environment, which I think I already have. So you have to export the OpenAI API key. For example, you have to go to your ZSH configuration.zsh rc here in this file and export your OpenAI variables. Okay, so you basically in the end of this file you have to type export OpenAI API key equals to your OpenAI API key, which you have to create from the OpenAI dashboard. There are instructions on how to do that, how to create an OpenAI API key and how to get the final token. And if you get that token, you just place it here. So we're gonna now create test if our API is working. So I'm gonna import OS and print API key ready. So if you do this, os.getEnv OpenAI API key. I think I'm missing one part. Yes. Yeah, API key ready, true. So because it can read OpenAI API key. All right. Now I have to choose the model. So I'm gonna export here OpenAI model, and I'm gonna set GPT-5 just for the sake of this test, but you can use anything else if you like. So yeah, I'm gonna export this. Now it's the moment of truth. I'm gonna run loop 1. Let's see if we get an error. I will be surprised if you don't get an error on the first try. Yeah, we got an error as expected. It is likely because we don't have a initial value here. I think we have to provide an initial value like running. So yeah, I think we missed adding that. Let's running it again. So the most important line in the output is gonna be the status. So success means the model eventually requested completion, and Python independently confirmed that the test passed. Blocked, stalled, or exhausted are also real terminal states. They mean the harness stopped the run for a reason instead of pretending the task succeed. So if this ends in success, I'm gonna do 2 final checks on the screen, the tests and the diff. But let's wait a little bit for this to finish its job. But I think it's better that we add some debug code so that we see what's going on. So in order to give it some, visibility of exactly, what's going on. So we first open. So in the loops.py, we're gonna add a new function like debug, and in this debug I'm gonna add a message like string that just prints loop and the message, and I'm gonna flush through. Yeah, then this flush through is actually useful here because you are watching the loop live, and it tells Python push the message to the terminal immediately instead of potentially buffering it. Of course, we have to move this on the top. This shouldn't be here, it should be in the top. So yeah, it's here. Perfect. Okay, after adding this, we're gonna add another function right after debug, describe action. And this is gonna have an action like this. And of course we have to import this from harness. This is gonna return a string. So if action.type equals to tool, we say detail empty, and if action dot name is in read file, write file like this, and then we do a path equals to action arguments path. So if path exists, then we say that the details are the path equals to the path, and yeah, else or elif action.name search code, we do the query. If query, then query is like this, something like this. And then we're gonna return action.name with the details. I think this parenthesis is not needed. Something like this, yeah. Yeah, this is for this if. And then if action.type equal to finish, then we just simply return finish. Nothing needed. Return blocked. Action.reason of blockage or no reason provided. What's missing is parentheses. Perfect. Okay. So this does not change what the agent can do. It just gives us a human readable description of each decision. So now that I have two small debugging helpers, I can add the message when the loop starts. So in the place where I define my run state, in here, basically I add a debug. I say starting model controlled loop, and then I add issue, or actually goal, here. Perfect. Then I also, for the place where I have my steps, for each step here. So now I want every pass through the loop be visible. This is particularly important because this is our first real feedback loop. So if the agent uses 3 tools before it finishes, I want to see step 1, step 2, step 3, rather than watching a wall of output with no sense of where I am. So I'm gonna add, after this part, after this iteration, I'm gonna add a debug message here saying step number of max steps. Very simple. Also, in the place where I do check budget, we do debug checking budget, and inside this exception, in case it happens, we do budget exhausted or budget stopped the run, something like that. Now comes to the model detection. Model decision. So I want a clear debug message immediately before the call, so we can tell when control leaves deterministic Python and goes to the language model. Right before this, we say debug calling the model, and right after this we say debug basically raw model response, something like that. Yeah. And we also want to, in the place where do the parse action, in case there is an error, we want to basically say debug invalid model action. Yeah. So this is another good debug message. And then after this try catch, it's gonna be another debug parsed action, basically. basically describe action. This is the one that we just created here. So also for the part where we do the blocked action type blocked, here we want to add a basically model reported blocked, and we do a plus describe action. Describe action. Yes. And also for the finish part here, we also do debug model requested finish, and right before this verification, of course, we can add another debug running verification tests. This is tool calls, by the way, not tools calls. All right, and yeah, then we get the verification results. Of course, we can add here verification results, but then it can be JSON.dump, because it's going to be JSON that's gonna be verification and also with indentation too. There's no F. Maybe I just write something like this. I don't understand what was the warning about. Okay. We just add this debug here, verification results. The part that we do exit code, I guess it's good that we add here verification passed, and I guess it's good that we say loop finished successfully. I still think this is gonna be nicer if we could just say plus JSON dumps and we pass verification and indent too. It would have been nicer if we do it like this. Perfect. I'm gonna add the place where it's been rejecting. Oh, this is also messages here. That say finish request rejected and tests failed. Right where we do this execution, right before this try catch, we can add another debug. We can say executing tool plus describe action, because it's a part where we call an action. I guess we can add an exception here, add a debugging here. The tool failed. I guess we can do another debug. We can say tool result JSON dump result. Also in the place where do the fingerprinting, why not we add another debug, say workspace fingerprint. Like we do plus fingerprint, let's say 12 characters. Perfect. Also in the place where do this stagnation, sorry. We can do another debug. Basically no workspace progress detected and loop is stalled. That's another. In the exhausted part, we can do another debug, workspace prod maximum step count reached, loop exhausted. Perfect. Okay, I guess now we can run this again with better visibility, hopefully. Step 1 of 20, calling get repository structure. Maybe make this bigger. Okay, list files, reason, spec repository. So it's now running the loop, and then you can have a good visibility of the steps. You get to check the budget, calling the model. Raw model response was get repository structure to locate stats implementation. And then we get invalid action type tool here. Okay, so if we go to maybe parse action here, I get action type. So if I, okay, this is why it's happening. I think here this is not the correct way of, it is not a list. This should be get args action type, and get arg supposed to be imported from typing. Yes, this should work. Let's run this again. Oh, what happened? Oh wow, for such a huge response, I guess what we missed probably was that we didn't add a correct harness. So it's walking through the entire project. I guess it also for whatever reason gets into the .vmv and .idea. So I guess we have to find a place where we do list files, and here, so in here, instead of this part, if .git in paths, we basically replace this with if any of ignored in path.parts for ignored in, and then I'm gonna give it like a dictionary, like a set of stuff, not only just git but also .git, .vmv, vmv, .idea, .pytest cache, everything basically we have in .git, and pycache. Yeah, if that's the case, then continue. Because what happened is the list started with all the changes. I'm just making sure that the test's still failing. Just one more time. Yes, I will also commit this before running. Initial changes. And then run this again. Python run loop 1. Okay. I guess this .ds sources should be here as well. Perfect. Also, in .git ignore, we have to add .ds store. I have to remove this here. maximum step counts reached. So let's go to the part where it says maximum. I think it's in the loops. Maximum step count reached, loop exhausted. Yeah, this should be outside the for loop actually. So I'm gonna add this change. All right, now I'm gonna run this again one more time. All right, we are getting somewhere. Check how, okay, now steps are okay. Final test. Okay, now work detected loop is stalled without any changes. So it seems like the loop is working, but then the problem is stagnation. So in step one, let's look at the step one. So in step one, the agents try to list the files. So it calls the list files. And in step two, it tried to read basically app.py. And in step three, it tried to read store.py. And in step 4, it tried to read models.py. And that's reasonable behavior. And then the model is now basically because investigating the repository, exploring the repository. But the fingerprints looks like this fingerprint is this C69D. This fingerprint is the same. So the fingerprints are the same. So that's our loop incorrectly concludes that okay, no work, no progress. So I think we should use this git diff stagnation only after write file, if a file is being changed, not for any other actions. So given that, we're gonna open the part related to fingerprint, and in this place where we debug fingerprint, and we're gonna append it here. This is the part that we have. This only happens starting from where we start to do the fingerprint. This only should happen if basically our action dot name is equal to write file. If that's the case, then we do the fingerprinting and all that. I think this makes sense. Only in this case, because then git diff matters. All right, let's try again. Maybe before we try again, I add this change. Stagnation. Okay. Now let's run the loop again. So step one, it starts listing files, and then it starts reading test stats this time, and then app.py, and then store.py. Yeah, now it starts to write the file to store.py. Final test, final diff. Sounds like, yeah, it managed to fix it. Now if I run the PyTest, yeah, 2 passed. So our loop is our first agent, and it managed to fix this in basically 9 iterations, 9 model calls, and 7 to do calls. It started by, as I said, exploring, and then in step 5 it started by executing a read. Then it started to invalid model action extra data line 1 column 163. There was an error here. Ensure other behavior expectation for to-dos, avoid breaking them. It probably returns a invalid JSON. This is kind of an invalid JSON because yeah, it has, there should be only one final bracket for author JSON. And then what happens is same error, invalid model action. It tried again, sounds like incorrect JSON, and next time it seems like it tried to write to the file and then it tried to execute the tests and it worked. With just one run it worked. But even though it didn't manage to create the correct JSON, it manages to fix the problem. But let's see why. Let's see if we can fix this. Model loop system. Here I basically in the end, or in the beginning even, I say return exactly one JSON object, one valid JSON object. Do not use Markdown, for example. Do not include any text before or after the JSON object. And make sure the JSON is syntactically valid before responding. Okay, we do a git status. I am gonna undo the changes here for store. I do the PyTest one more time, one failing. So git add, git commit, strengthening. Okay, and I'm gonna run this again. Let's see. Okay, listing files, reading app.py, reading store.py, reading test.py. Okay, reading test create to do without any issues. Step 6 is reading models.py. Step 7 is confirm failing test. It is failed. Step 8 is writing something to store.py. Step 9 is verify the changes. And the changes happened. Pay PyTest queue without any important error. So we had our first loop running correctly. Now I'm going to stop the implementation here for this episode. There is going to be a follow-up episode which we're gonna go through many other types of loop engineering architectures. If you want to follow the experiments, please subscribe and like Softwareify AI Talks, and I will see you in the next episode. I'm your host, Michel Gokan, and thanks for listening.